Hello. Uh, Last week we have discussed about stream ciphers. Uh, as a summary, I would again recall you what we have discussed. So stream ciphers are they are constructed to follow or something like to get the similar characteristics of one-time pad, but we know that one-time pad is not possible in the real world because uh, the challenging thing is the key stream should have the same length as the message. So for a bigger bigger messages, it's very challenging to manage the key stream. To pass that hurdle, these stream ciphers are constructed in a way that they can generate a key stream using a small key or a seed value uh, in a way that it looks random. So we call key streams a pseudo-random uh, thing. So that's the story to start, or the coming to the topic of stream ciphers. And then we have discussed about some characteristics of stream ciphers. So there are two types of stream ciphers: synchronous and self-synchronous. So in this course we are talking about synchronous stream ciphers only. That means both the send and the receiver has the same clock, same speed, and we know that how the stream ciphers work. It does the XOR operation bit by bit uh, using the plain text bits and the key stream bits and generate the ciphertext bit. And then the major component of design in stream ciphers is the linear feedback shift registers. They are just shifting the bits upon the clock triggers, and combining the outputs from each point will generate will help to generate a pseudo random key stream. So for that we call recurrence relation is how we combine the bits of the key, the linear feedback shift register, and generate the output the key stream. And when we're talking about the linear feedback shift registers, we have to talk about the period of the key stream and also the linear complexity of the key stream generated. And then we discussed about attacks on stream ciphers if the period is lower and if the linear complexity is lower. Okay, so those are the things we have discussed so far. And also we talk there are three properties that we use to measure the strength of a keys of a uh, key stream, or key stream is generated from a stream cipher. So basically to measure the strength of a stream cipher. So large period should be there, larger linear complexity should be there, and we discussed those things. And another thing is the random noise-like characteristic should be there when the key stream is generated. It should be like it should close to a random stream. That's the idea. So we haven't discussed about that yet. So today I'm going to discuss about that part. So noise-like characteristics. So in order to avoid the statistical analysis by an attacker, the key stream should have noise-like characteristic. That means it should look like a random. So it will avoid the attacker to statistically analyze the key stream and predict the next bit of the key stream. If he can do that, then he can generate the key stream from that point onwards. Okay, so defining and measuring the randomness is very difficult. So there are three basic properties to measure the randomness of a periodic binary sequence, which was defined by Golomb in 1967. Golomb is a mathematician, so uh, defines he defined basic properties to measure the randomness. So then we can say, okay, according to the Golom's definition, we can measure that this particular key stream is either random or not, or closer to random or not. A periodic binary sequence which satisfies these three properties is said to be G-random. G-random means if the key stream is satisfying the three properties defined by Golomb, we can say that key stream, that particular stream, is a G-random key stream. So Golomb's postulate, it's like this. G1, the first thing is approximately half of the terms in a periodic should be 1. So that means ones and zeros should be, there are same number of ones and zeros. Not the same, but very closer to the same. Half of the bits are 1, half of the bits are zeros. In a period, half the run should have length 1, 1/4 length 2, and so forth. We'll discuss about this thing. And the third one is the output phase autocorrelation function is constant. Autocorrelation is that value should be constant. So autocorrelation is computed A minus D divided by P. That A, D are the numbers of agreement and disagreement of the cyclic periodic sequence with the original periodic sequence, and P is the period length. So we will discuss about that thing, taking an example. So consider the following sequence. So here there is a sequence 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30, 31. 31 bits are here. So numbers of ones 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. There are 16 ones. That means half of the sequence is ones. And number of zeros 15 out of 31. So half ones and zeros. So it satisfies the G1. And G1 is satisfies. And example run lengths. So runs are the things like we can say this is 1. And after the 1 we have a 0. So this run is length 1 run. This is length 1 run. After that we change the bit. And this is 3 zeros. That means the length is 3 zeros, 3 before it change the bit. Then 1 comes. So this run is 3. And here the length of this run is 2. That means 2 ones, and after that the bit will change likewise. So length 1 runs are 8 length ones run. Here 1 and 2, 3, 4, 5, 6, 7, 8. So 8 length 1 runs like that. And length 2 runs 1, 2, 3, 4. Length 2 runs are 4. And length 3 runs 1, 2, 2, only 2. And length 4 runs 1, only 1 and 1 here. And length 5 runs 1, 2, 3, 4. Length 5 runs. Where are the length 5 runs? 1, 2, 3, 4. There should be 1. Anyway, so it should look like, so length 1 runs, here it says approximately half the runs should have length 1, 1/4 length 2, and so forth. So half the runs. Total runs are here 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17. There are 17 runs. Runs means the same bits before changing the bit. So that means same some number of zeros before changing it to 1, some number of 1 before changing it to 0. They are the runs. So there are 17 runs. From that, length 1 runs are half, approximately the half. That means 8. Length 2 runs should be like approximately it should 1/4. There are 4. Length 3 runs 1/8. So likewise. So that should satisfy approximately to satisfy the G2 postulate. And cyclic shift of the periodic output. So that means when we we have the key stream like this, and we do a cyclic shift to one direction, shift to left side. So when we do a shift to left side, that means this the key stream shown in the line 1 will do a shift to left. So everything will give a left shift, sorry, right shift, and the one of this rightmost corner will come to the leftmost corner. So when we do that shift, then we compute the agreements and disagreements. So consider the line 1, and then line 2 is one shift to the right. So then we can, everything will be shifted to one bit to right, and the rightmost bit will come to the leftmost position. So then the number of agreements. So 1 and 1 agree. Here 1 and 1 agree, and here 1 and 1 agree. So, like that. Number of agreements. There are 1, 2, 3, 4, 0, 0. That means 5, 6, 7, 8, 9, 10, 11. So there are 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 13, 14, 15 agreements. 15 agreements are there, 16 disagreements. Disagreements means when the bit of that particular position is 0 in the previous sequence, and cyclic shift will give you a 1 to the same position. So that means a disagreement. So disagreements are 16 because there are 31 bits, 15 agreements, 16 disagreements. So that value should be the value we call out of phase autocorrelation value. That will be here A minus D, agreements, number of agreements, minus disagreements divided by P. P means period. So 31. It will be minus 0.032 something. And then we do another left shift, another right shift to the second stream we get, and then we measure the same out of phase autocorrelation. So that should be so when we do bit by bit right shifts, this value should give same out of phase autocorrelation, like approximately the same value. So we can say it's a constant. So it should be a constant value. So if these three conditions are satisfied, we can say our key stream is G random. So if it is G random, we consider it as a random sequence. So that means we can say it satisfies, or it looks like a noise like thing, look like a random. So if the period is higher and the linear complexity is higher and looks it is G random, then we can say okay, this stream cipher is a strong stream cipher. Okay, so after that let's have a little bit of discussion about the maximum length sequences. The maximum length sequence, or M sequence, is a sequence of length 2 to the power m minus 1 which contains every non-zero binary sequences of length m. So which contains every non-zero binary sequences of length m. If you have a length m sequence, non-zero zero binary sequence means all the m bits are zeros, and non-zero means either one or more bits are non-zeros. So theorem, any M sequence generated by an linear feedback shift register of length n satisfies the following three properties. Period is 2 to the power n minus 1, its linear complexity is n, and it is G random. So any M sequence, so maximum length sequence generated by a linear feedback shift register of length n satisfy the following three properties. This is theorem. So M sequence should not be used by itself as a stream cipher since it has a smaller linear complexity in comparison to period length. So when we take an M sequence or the maximum sequence, it should not be used itself as a stream cipher because it has a small linear complexity. Small linear complexity, that means it is possible to attack. Okay, so so we have to consider this theorem when designing stream ciphers. So any M sequence generated by length n LFSR satisfy the following things. It is G random, its linear complexity is n, and period is this thing. So let's now discuss about few examples of stream ciphers. One of the famous thing is A5 cipher. This is stream cipher. It's a binary synchronous stream cipher applied today in most GSM mobile telephones. So A5 has three variants: A5.1, A5.2, and A5.3. There are some implementation differences, and these are the variants. The design of A5.1 was originally kept confidential by its designers but became public in 1994. So mostly these stream cipher kind of things are used in places where we need confidentiality when data streaming. So we can use them for mobile networks or like television streams or radio likewise. And this is the design of A5 stream cipher. We don't need to take this into a very serious level. You just read about this and get familiar. And RC4 is one of the most famous and widely used thing. This is used by Ron Rivers. He is one of the most popular cryptographer in the world. You will hear this name when you learn cryptography further, especially when you learn about public key cryptography. So he is very famous in for RSA encryption scheme. We'll discuss that later time. So this RC4 stream cipher, this is a symmetric key scheme. It is also generated by Ron. So this is simple and efficient software implementation. Originally owned by RSA Security. RSA Security means that is based on that's a company. Uh, so their main product is RSA encryption scheme, which is a public key encryption scheme. But leaked in 1994, widely deployed, including TLS, WEP, and WPA. So TLS is the cryptographic protocol suite we use for our internet communications. When you have HTTPS, that means our data transmissions go through this TLS protocol suite. Example of a word-based stream cipher, and plain text is broken into 8-bit words, that means bytes, and key stream output is a word. Word means 8 bits. Ciphertext word equals plain text word XOR by key stream word. So this operate on word level, that means not bit level, 8 bits level. So as a summary of this thing, you have to know about what the stream ciphers are, what is the difference between stream ciphers, or let's say like not the difference because we didn't discuss about other things. Uh, what is the way that these stream ciphers do encryption? You have to understand that really well, and about one time pad, and then you have to understand about the properties of how to measure the strength of a stream cipher using these three measures, and then attacks on small period and attacks on uh, smaller linear complexity. So you have to get familiar with those words as well, linear complexity, period, like things, and understand this thing. You can you can understand this how to attack low linear complexity just by looking at this example and do it 1 and 2 times by yourself. And then how to measure the randomness. There's no way to measure the randomness, so Golomb he proposed a way to measure the randomness using Golomb postulate, saying Golomb postulate. So if a key stream satisfies the three conditions of the Golomb's postulate, we can say that stream is G random. That means that is according to the Golomb postulate. So this is the three conditions of that, G1, G2, and G3 things. And then just have an idea about maximum length sequence and know this theorem. And then you have to know about the examples of stream ciphers and the uses of them. Okay, so this is all I want to discuss about stream ciphers. You have to have a basic understanding about these things, and I will upload an assignment, so you can that's a group assignment, so you can try that and get more understanding about the things we discussed, and you may have to read some more from the internet to do the assignment. Okay, so next week we'll discuss about block ciphers. So that's again a kind of that is again in the category of we call symmetric ciphers. So the symmetric ciphers are the ciphers that the sender and the receiver both needs to share the secret key, or the encryption and decryption key, both are the same values before the use of the system. So stream ciphers are one way, block ciphers are the other way. Stream ciphers, they operate on bitwise or wordwise, anyway that supports the streaming of data. But block ciphers are not like that. they are not supporting very much supportive to streaming. uh, it take a block by block and do the some kind of a some expensive operation, we can say expensive, or like it uses more computational power for that, not a simple like stream ciphers.